Hi, my name is Stuart Williams, and this is the second in a series of short Azure videos on different facilities inside of Azure. And today we're going to talk about Azure Storage. Azure Storage general purpose accounts. An account is an umbrella over different kinds of storage assets. Storage assets are stored in different containers, tables, queues, shares, and disks, depending on the type of asset. And so in this table, we see what the containing object is called. And then we see downstream from that the type of object that's installed inside the container. Blobs can be used to store any essentially collection of bits. Blobs can have an associated file name and other metadata. Blob storage has many charming features, which we'll get into. Table storage is effectively a NoSQL database, currently part of Azure Storage, but will become subsumed into Cosmos DB towards the end of the year and will offer more functionality and scale. But that being said, table storage and the entities therein will continue to be very useful. NoSQL structures. The virtue of NoSQL databases, of course, is that they allow for schemaless or dynamically defined schemas in storage. And so you can create within a single account any number of Azure tables. Each table has a consistent storage schema, and you can query them using the API or the REST API. When they become subsumed into Cosmos DB, doubtless they'll be facaded by additional APIs, including the API from MongoDB, which will be very handy for many developers who are used to developing against the Mongo API. Queues are the storage mechanism's queue implementation. And although there are lots and lots of queue types up on Azure, which we'll cover in a future session, this is the one based on storage. Because these queues are in storage, the messages are easy to inspect, and they obey the appropriate queue semantics while also allowing you to peek at messages stored in the storage. The fourth type is called a share, and shares represent a mountable file system of files and folders. You can mount these from Linux or Windows file systems. It is mostly intended to be used for programmers, but you can build things on top of that that benefit from file and folder tree structures. And lastly, the disk type of storage, which is the place where Azure virtual machines and containers and other types of similar infrastructure as a service things store their images, and the Azure Storage account allows these to be managed and has facilities to then interoperate with container engines and VM engines in order to serve up these disks to form running machines or running container stacks. So these are the fundamental building blocks available in Azure, and them you can address any number of useful business scenarios. There's also another kind of storage account called blob storage accounts for scenarios where you only need blobs. You don't need table storage. You don't need queues, disks, files, folders, or any of the other accoutrements. And they're specifically intended for either high performance at a slightly higher cost or low performance at a lower cost scenarios referred to as the hot storage tier and the cold storage tier. And you can see their availability in local redundant storage and geo-redundant storage respectively, and they have similar performance characteristics. And cold storage particularly is a useful tier for organizations that have big chunks of data, maybe archival log files or flat files, web logs, structured or semi-structured data that you want to store cheaply and then go after using your favorite analysis tool, whether that's Data Factory or HD Insight, or even consuming them from things like Power BI directly. The cold storage tier is probably the cheapest place to store objects up in the cloud. Azure offers 4 kinds of storage redundancy. The basic one is called locally redundant storage. So within a single data center, what they're promising is that they will replicate your data 3 times, and they'll do it in such a way that the failure of any one component in the data center, say the power supply to an entire rack, for example, won't result in loss of data. So they're distributing your data within the same data center. Data centers come in pairs, and those pairs are called zones. Some zones actually have 3 data centers in them, but for the majority are in pairs. And so if you want storage to be replicated across 2 different data centers, and data centers pairs are always at least 301 miles apart, then you have a scenario where the data is stored 3 times, and the loss of a data center won't result in the loss of your data. That's zone redundant storage. So if you want to store data across zones, that's what geo-redundant storage is. And geo-redundant storage is actually replicated 6 times across 2 different regions. So you can think of a data center belonging to a zone and a zone belonging to a region. And now we are distributing our data across 2 different regions. And these are extremely durable ways to store data that makes loss other than deliberate deletion almost impossible. The one thing to take note of as you go down the storage redundancy tree is to make sure that, particularly as you move to geo-redundant storage, that you are obeying the data sovereignty rules in your jurisdiction. And the European Union, Brazil, and other places, China, have very specific data sovereignty rules. You want to make sure you don't inadvertently break those by using geo-redundant storage. And lastly, the utmost in storage redundancy is read-access geo-redundant storage, which is exactly like geo-redundant storage, except that you can actively do reads from the second region. And what that means is that if your 2 regions are linked together in geo-redundant storage, that the users in the second region will be able to read from the data center that's got the lowest latency for them. And so with a little bit of setup and clever architecture, design, and implementation, not only can you have geo-redundant storage, but you can do something to optimize your read performance as well. So data consistency models are super important. For Azure, writes are what's called immediately consistent, assuming the write takes, and we'll get to that in a minute. But if the write is successful, then they're done using a transaction model called snapshot isolation. So when the write mechanism is invoked, the call will only return when the write is complete. And the other thing about that is that when you have a write, readers will immediately see the changes. 2 things about that. One is, obviously, because of latency reasons, above locally redundant storage, there may be some write latency from zone to zone or data center to data center, and certainly in geo-replication scenarios. But that being said, the data will be for readers or located in the same data center. Writes will be consistent with the reads. And that's what snapshot isolation is all about. And you can read more about it on the link that I gave you. It's important to notice, though, that not all cloud storage providers use immediate consistency. In some cases, like Amazon's S3, the writes are eventually consistent, and that means the call returns, but the data may not be fully written or distributed to storage, which means that reads can be inconsistent. That is to say, the reads, if I write record A and then read it, I may not see the changes right away. And this is tunable on most of the cloud platforms, but you have to understand it's happening in order to tune it. And as a resource, we've included the storage FAQ URL, so you can go look and see how that can be tuned on S3. Neither one of these things are superior. They have pros and cons, but the most important thing is to know what data consistency model is being applied to your storage and understanding the differences in behavior that brings. One other note is that once table storage is subsumed into Cosmos DB, table storage will have all 4 of the Cosmos DB consistency models. We're going to cover Cosmos DB in a future session, but you can read about consistency levels in Cosmos DB following the link. Data concurrency is about optimistic, pessimistic, and none-locking. By default, Azure Storage does last one in wins, or essentially no locking. In optimistic concurrency, when we read an item from storage, we get an E tag. And if, as we write that item back, the E tag that's in the storage currently for that item and the E tag we're trying to write don't match, we know that the data's changed from underneath us, and we'll get an error back indicating that we have an optimistic concurrency failure. The rest code for this is 409, and it materializes as various exceptions depending on what API you're using. Pessimistic concurrency uses a locking mechanism, which is to say we explicitly attempt to lock a record. The locks, as most locking mechanisms do in the cloud, are actually a time span that we're asking for exclusive control over the record. And assuming that someone else tries to write your record while you have it locked, they'll get an error. And if the time span has expired, they'll be allowed to write, and you'll see an optimistic error if then you subsequently try to write. So you have the choice of 3 concurrency models, none, optimistic, and pessimistic, that you can tune for your scenarios. Performance. As we've called out, especially for blob storage, there are a number of choices, hot versus cold on pure Azure storage accounts, and so on. And a big factor for performance is typically the design of the keys used to do storage. A poor design, or a design that spreads out too broadly too quickly, will result in very sparse reads, and that will have an impact on performance. In the scenario where our key space is too narrow, when we do writes, we'll actually create hotspots as we try to write adjacent storage locations, and this is particularly noticeable if we're doing a lot of writes in a very narrow range of keys. So key design along with storage types are 2 considerations. Another consideration is using Azure Content Delivery Network, a CDN, to help performance. Significantly, this is most suitable for blobs, especially public blobs. That is to say, blobs that we provided a public URL to that we might use as a reference on a web page. Facading that with the CDN will significantly improve the performance because now we're reading from the edge network and not necessarily from the Azure store. Likewise, if you adopt a command and query responsibility segregation, or CQRS pattern, you can result in better performance, especially if your system is very tolerant of, or moderately tolerant of, write delays being mediated by a queue. One of the downsides to Azure's immediate consistency model is that writes can be slower than on comparable systems on other clouds. The advantage, though, is that if your system can tolerate differential reads and writes, especially having your writes be queue mediated, can have 2 significant benefits. One is that your system will be very tolerant of bursty scenarios because the queue will take the sting out of suddenly getting a bunch of write requests in a bursty way. And the second is that if the records need to be processed in some way before they go into storage or into a form that can be read, this provides an opportunity to insert a processing pipeline into the write or read parts of your architecture. Security model. Fundamentally, two core security models for assets in Azure Storage. One are storage access keys, and typically there's two of these for each storage container, and they give carte blanche access to Azure Storage resources and are typically used by administrators or by highly trusted components up in the cloud that are part of your solution. Storage access keys are intended to live for a long time, although you can implement a policy by wherein storage access keys are regenerated, in which case every place that you use them, you'll have to go and fix them up. But they're the simplest key mechanism, and you can get the storage access keys right off the portal. Shared access signatures, by comparison, are a type of security token that you can be very granular in specifying not only permissions, but how long the token lives. And those have to be generated by calling an API. In other words, they have to be part of a code chain. But shared access signatures have the advantage that you can hand out access signature tokens on a very specific object for a defined lifetime, and you can control very granularly what types of operations can be done against the item in question or items in question. In that way, they act a little bit like ACLs in operating systems. If you keep track of who you issued the shared access service tokens to, you then have a method for doing logging and an element of repudiation protection. It's not unusual to facade a intermediary over the top of storage in one way or another. And there are a bunch of ways of doing this, including putting a service between the consumers and storage directly. But another popular model is the intermediation pattern, where the client has a secure conversation with an API up on the cloud using whatever security mechanism you would like. If that conversation is successful, the web API will ask the storage engine to give it a shared access signature token, and then that's passed back to the client, and the client can then use that shared access signature token until the token expires or is revoked. APIs. All Azure services are facaded by a restive API. And because it's facaded by a restive API, different teams, including teams at Microsoft, have gone along and wrapped the REST API into something a little more object-oriented or procedural-oriented. So tooling. Two fundamental sets of tools available from Microsoft. One is AZ Copy, which is designed to be a command line facility in either the DOS command PowerShell or Bash that you can use to very efficiently copy things into and out of the cloud. It's very handy for developers who are loading up data sets or for moving large volumes of data into, for example, cold blob storage from inside of your enterprise. The other is an interactive tool called the Azure Storage Explorer, which is a free download, and that allows you to have a GUI that you can use to inspect the contents of your storage account and manipulate the data inside of it. My name is Stuart Williams, and I work at Magenic.